Hello, this is my differential equations exam for review problems and solutions video. We're going to start off with a problem related to damped forced harmonic oscillators with sinusoidal forcing, ultimately looking at the forced response or steady state solution, its amplitude and phase. From there, we'll move on to a nonlinear system, a competing species model, focusing on the idea of linearization with the Jacobian matrix. After that, we'll look at some problems related to linear systems, a bifurcation problem with a family of linear systems, and also something related to the spectral theorem in linear algebra related to orthogonal diagonalization. And finally, we'll end with some true, false, and multiple choice questions, some of which are related to Hamiltonian systems and gradient systems. So here's the first problem. Consider the following forced damped harmonic oscillator equation. The second derivative of y with respect to t plus 6 times the first derivative plus 25 times the function itself doesn't equal 0, it equals cosine of 2t. Cosine of 2t is your external forcing function. This is a forced damped harmonic oscillator. It's a lot of work to solve equations like this, so I do some things to help my students along the way and also help me with the grading. Part A says, show work to confirm what the answer should be for what's called the general solution of the corresponding homogeneous unforced equation where the right-hand side has just a 0 instead of a cosine of 2t. Show that that function is the solution right there, the general solution. Okay, so you need to know how to do that. Quick way to actually show your work on that is to go ahead and, let's go ahead and write down the unforced equation in prime notation. Y double prime plus 6y prime plus 25y equals 0. What we do is we essentially guess. We guess a solution of the form y equals e to the st for some unspecified constant s, and you've got to figure out what s is. Now it turns out, in this example, s ends up being a complex number, and because of something called Euler's formula, that's why we get this general solution that involves not just exponential decays, but also trig functions. In order to find s, you've got to take the derivative with the chain rule with respect to t. We get an extra factor of s each time we take the derivative. There's the first derivative, here's the second derivative. We plug those things back into the differential equation. I'm not going to show you the details of some steps here, but ultimately you're going to get down to a quadratic equation in s. S squared plus 6s plus 25. You can check those steps on your own. This has got to equal 0 in order for e to the st to be a solution. This is the corresponding characteristic equation for the linear system that you could create from this second order equation. If you use the quadratic formula to solve it, you get s equals negative 6 plus or minus the square root of 6 squared is 36, minus 4 times 1 times 25 is minus 100, all over 2 times 1. That becomes negative 3 plus or minus, this becomes square root of negative 64, which is going to be 8i, where i is the imaginary unit, divided by 2, that's going to give us plus or minus 4i. So negative 3 plus or minus 4i are the values of s that make this function, this complex function in this case, a solution of this real differential equation. To create a real general solution, we need to use Euler's formula to expand this complex solution and take the real and the imaginary parts of the complex solution as the things that we make the linear combination of here to get the general solution. So what do? It's actually good enough just to take one of the eigenvalues here, negative 3 plus 4i. I'm saying eigenvalues because it does, again, correspond to a matrix. Multiply times t, expand this out. That becomes e to the negative 3t times e to the 4it, or if you prefer, I times 4t power. And then Euler's formula, Euler's identity, says this thing right here is cosine of 4t plus I sine 4t. When I multiply the e to the negative 3t through that, I get e to the negative 3t cos 4t plus I e to the negative 3t sine 4t. We're almost done. That's our complex solution expanded. How is it related to this one? Essentially, we take this thing right here and this thing right here without the I, call this, say, y sub re, real part, and y sub im, imaginary part, but they're both real quantities. The imaginary one's just next to the I. Those are linearly independent solutions, it turns out, of the original unforced real equation, and a general linear combination of them will be the general solution, because it turns out the solution space of this is a two-dimensional vector space. So we get general solution, go ahead and call it y sub h for homogeneous, is k1 times the first function y re, that's e to the negative 3t cos 4t, plus another arbitrary constant k2 times the second function y im, that's e to the negative 3t sine 4t. Okay? My students, you wouldn't have to actually explain that. I did verbally explain how you get from here to here, but you do need to know we don't want a complex solution in the end. We need to get rid of the I. We take these two real solutions, you can confirm they are real solutions of the original unforced equation, and take a linear combination of them. And that will be your general solution. On to part B. Part B, the corresponding complexified equation is a forced equation, non-homogeneous, where the right-hand side is e to the I times, well, in this case, 2t power to match the 2t right there in this forcing function. If this was cosine of 3t, then I'd put a 3t there instead. Once again, I'm telling them the answer to save time, to save work for me in grading. Show work to confirm that this function, this complex function, notice I is there still, solves the complexified equation, this one right here, when the a is this complex number right here. Sorry, I crossed the numerators there. A equals 7 over 195 minus 4 over 195i. So I'm telling them what the answer is. If, as a student of mine, if you can't quite get that answer, you can still go on to the next part, part C and D, and answer those based on knowledge that this is the true answer for part B. So how do we do this? It's once again a matter of differentiation, substitution, and some algebra. There's our yc. I'm calling it yc because it's complex. It's an undetermined coefficient that ends up being a complex number, times e to the I 2t. Don't use Euler's identity now, just differentiate. It's easier to differentiate with an e instead of cosines and sines. So we get an extra factor of 2i each time. So I get 2i a e to the I times 2t power for the first derivative. For the second derivative, I get another factor of 2i. 2i times 2i is 4i squared. I squared is negative 1, so that becomes negative 4. A e to the I times 2t power. Let's be a little more careful here in substituting this into the complexified equation here. Go ahead and take the second derivative, add 6 times the first derivative, plus 25 times the function itself. It's worth being careful here. This is going to be the negative 4a e to the I times 2t, plus 6 times the first derivative, 6 times this thing, is going to give you a plus 12ia e to the I times 2t power, and then plus 25 times the original function, that's plus 25a e to the I times 2t power. We want to factor out anything that can be factored out. Each one of these terms has an a, and each one of them has an e to the I times 2t power. When those two things are factored out, what's left over are numbers. A complex number, in fact, with real part equal to negative 4 plus 25 is 21, and imaginary part 12. But you do need to put the I there. I want to set this equal to the right-hand side of this complexified equation, e to the I 2t. Set this equal to e to the I times 2t power, which is really 1 times e to the I times 2t power, which means that this thing right here must equal 1. And so a must be 1 divided by 21 plus 12i. Therefore, a is 1 divided by 21 plus 12i. It's a good idea to, and in fact to finish the problem, we need to write this in standard form, and the trick is to multiply the top and the bottom by the complex conjugate of the bottom. That doesn't change the complex number itself because you're really multiplying by 1. And when you multiply a complex number times its complex conjugate, it does have the benefit of being a real number. That's the magic here. Because when you excuse me here. Oh, my calculator's not working here. There we go. All right. When we FOIL this, first times first, outside times outside, inside times inside, and last times last, the outside and inside terms cancel, right? Because 21 times negative 12i is going to cancel with 21 times positive 12i. So you're left with 21 squared from the product of the first two terms, 21 squared, 441, plus 0, and then minus 112 squared times I squared, minus 144 I squared is plus 144. 441 plus 144 is 585. So this becomes 21 over 585 minus 12 over 585 I. Is that the same as what we want? Not quite. We need to reduce the fractions. Every one of these, the numerators and denominators here are divisible by 3. This does simplify to 7 over 195 minus 4 over 195i. That is the value of this complex constant a that matches what you see there. Okay. On to part C. Use part B and Euler's formula again to help you confirm that a particular solution yp, p for particular, of the original, going back finally to the original equation way up at the top here, the original forced damped harmonic oscillator is this function right there. This is this thing called the forced response or steady state solution. It's not an equilibrium solution. It's not a constant function. It's the long-term steady state when you've got damping, because the YH here, no matter what K1 and K2 are, it's going to go to 0 as t goes to infinity because of the exponential decays. So it ends up approaching yp, the sum of the two things approaches yp as t gets larger and larger. That is what you actually observe in the long run. Okay, so we want to do that. We want to use Euler's formula. Well, how do you do that? We use part B. We use this yc function, this function right here, when a is this, right there. And because, here's the key, because the right-hand side of the original forced equation is cosine of 2t, we end up taking the real part of that product, the real part of this thing when a is this, and that will be the answer. If the forcing function had been sine of 2t, then we'd take the imaginary part of this function as yp. Okay? If it's a cosine, take the real part. If it's a sine, take the imaginary part. So we really just need to do a calculation that confirms that the real part is what you see right here. Okay? It's not too hard. Yp, let's go ahead and write it this way, is the real part of yc, again, because the forced equation, the original one, is a cosine. If it were a sine, we take the imaginary part. So it's the real part of this product of this number, 7 over 195 minus 4 over 195i, times, excuse me, e to the I 2t. Here's where we use Euler's formula. Replace that with cos 2t plus I sine 2t. Now you can save some work here by realizing the real part is just going to come from F and L from in FOIL, first times first and last times last. You don't have to do outside times outside and inside times inside. For the sake of completion and also for the sake of just remarking what the answer would be if the original forced equation involved sine of 2t, I will go ahead and expand the entire thing out. Yes, the real part comes from first times first and last times last. Let's write that down first. 7 over 195 cos 2t. And last times last, I'm going to get a negative I squared in there, which is going to be positive 1. So I'll get a plus sign. Plus 4 over 195 times sine 2t, last times last here. That is actually the real part of what I'm writing here, and that is yp right there for our problem. You can see it does match that. But let's, for the sake of completion, again, go ahead and multiply outside times outside and inside times inside. The I I'm already factoring out, so I'll get, let's write the cosine term first. Negative 4 over 195 cos 2t, and then that's from the inside times inside. Outside times outside is going to be plus 7 over 195 sine 2t. So yes, yp for our problem here is just what you see right there. 7 over 195 cos 2t plus 4 over 195 sine 2t. And that does confirm what we wanted to confirm right there. That is the yp. Once again, for emphasis, if the original force equation had been sine of 2t, the answer would be the imaginary part of this. It would be this function right there. Okay? But we have a cosine, so we take the real part. That's the confirmation. Last part, part D. Find the amplitude, capital A, and phase angle, phi, of yp, this forced response, this solution that is what we observe in the long term. And here's where, well, you know, the complex number approach to this has a number of benefits. One benefit is it's easy to do calculations with exponentials. Another benefit is that you get two solutions for free of two different differential equations, one with a cosine of t on the right side, one with a sine of t on the right side. Another benefit, when you take the complexification approach, is the A, this complex constant, contains information in it about the amplitude, capital A, and phase angle, phi. Let's draw this number in the complex plane. What is the complex plane? Well, it is a plane where we imagine points in this plane as being complex numbers. We call this axis the real axis, and this one the imaginary axis. And we use a rectangular coordinate system and plot complex numbers in this plane. For example, if this were the number 2 right about there and 1 was right about there, a point right about there would be 2 plus I. 1 would be here, I would be there, negative 1's here, negative I down there, etc. Of course, this number is pretty close to the origin. On that kind of scale, you're going to be able to barely distinguish it from the origin. So I have to imagine expanding the scale so that 1 is kind of far away from the origin. So 7 over 195, the real part of this is positive, and the imaginary part's negative 4 over 195, negative. So something, say, right about here. I'm imagining this number here is 7 over 195, and this one on the imaginary axis, as far as the rectangular coordinates go, is negative 4 over 195. Of course, as a complex number, that would be negative 4 over 195i, and maybe I should label it that way, thinking it as a point. But the complex number we're after, this is the A, is right there. And it turns out that the amplitude of the force response, capital A, is the distance between little a and the origin. And you can use the Pythagorean theorem to figure that out. Okay? That distance, the hypotenuse, is capital A. And the phase angle, which is related to the horizontal shift of the graph of this function from an ordinary cosine wave, it turns out, is this angle right here. And you do want to think of that in this context as a negative angle. It's the most common thing to do, at least. So that is phi, that angle there that's going from the positive real axis down to this line there. Just try to make a little arrow there. And so once again, you can use, well, the Pythagorean theorem and trigonometry to figure this stuff out. So turns out capital A, the amplitude of the force response, is the distance between little a and the origin. That's typically written as the absolute value of A, also called the modulus of A. And it is, by the Pythagorean theorem, the square root of 7 over 195 squared plus negative 4 over 195 squared. Let's go ahead and simplify that. There'll be a common denominator of 195 squared. And then when you take the square root of that, you'll get 195 out in the front. And with the 7 and negative 4, you're going to get the square root of 49 plus 16. So that'll be the square root of, what's 65? Okay. That, I think, is correct here. Let's just see what it is approximately. Square root of 65 divided by 195 If I recall correctly, I'm pretty sure this answer is right. I don't think I've made a mistake. About 0.0413. Actually, I will use Mathematica to check my answers on this sometimes. And then with the phase angle, it turns out that the tangent of the phase angle is going to be the imaginary part divided by the real part. And when you divide this by this, the 195s cancel, and I get -4/7. As long as the real part is non-zero, as long as you're not on the imaginary axis. If you're on the imaginary axis, then you just look at the picture to see what the angle is. This is going to be something we can solve for phi in terms of the inverse tangent function, inverse tangent of -4/7. You do need to be careful sometimes. It's possible that the A could have been over here in the third quadrant, and then the inverse tangent function would give us an answer, in that case, actually in the first quadrant, and you'd have to subtract pi radians from that to get to the third quadrant. But in this case, this should be fine here. I am in radian mode here, and now go back and do the inverse tangent of -4/7. In radian mode, that's about -0.519 radians. Multiply that by 180 divided by pi to convert to degrees. That's about -29.7 degrees. Okay. Let's see what all this implies about the graph. So those are the answers. Let's see what all this implies about the graph of the solution. Here is the graph of the solution. I made a graph ahead of time of the steady state solution, YP, forced response. It is, you can see a sinusoidal graph, a cosine wave, you might say, shifted to the right by a certain amount. Amplitude a little bit bigger than 0.04, so that looks good. And horizontal shift, a cosine wave always starts at its peak, so it's a horizontal shift to the right from an ordinary cosine wave by about 0.25 units. And in fact, what we've done here is YP can also be written here as capital A times cosine of 2t plus phi. And we found that this is approximately 0.0413 cos 2t minus, use the radian one, 0.519. And if you factor out 2 out of both terms inside the parentheses here, you'll be left with t minus 0.519 divided by 2, which is close to 0.25. 0.519 divided by 2, about 0.2595, rounded to 0.26. And that does represent a rightward shift by close to 0.25 of the cosine wave, okay? So that's what all this means. Oh, all right, on to problem number 2. This one looks long as well, but I think it'll go a little quicker because, once again, I do things to save some work. It's a competing species model. dx dt is some function f of xy. dy dt is some function g of xy. Because those right-hand side functions don't depend on time, we call this an autonomous system. And that makes the phase plane easier to think about. It's static, phase portrait. It is a competing species model. X and y are species. In the absence of y, if y is 0, the dx dt equation, this term goes away, and you're left with a logistic model with a carrying capacity of 5. In the absence of x, if x is 0, in the dy dt equation, this term goes away, and y follows a logistic model with a carrying capacity of 4. Now, the units for x and y are probably like in thousands or something. When I say 5, I mean 5,000. When I say 4, I mean 4,000. These two terms that are there when x and y are both positive, they affect things in that case. Both have negative coefficients, and when x and y are both positive, as populations have to be, they're going to negatively affect the growth rates. These species are competing. Okay, so this is how the model's usually written initially. To find equilibrium points, to draw the phase portrait in the phase plane, it's good to factor these things as much as possible. In the first right-hand side, each term has a common factor x that can be factored out. And you're left with 10 times 1 is 10. 10 times negative x over 5 is negative 2x. And if you factor an x out of this one, you're left with negative 5y. And then with the second right-hand side, each term has a factor of y that can be factored out. You're left with 8. 8 times 1 is 8. 8 times negative y over 4 is negative 2y. And factor y out of this one, you're left with negative 3x. It's this factored form that makes it easier to find equilibrium points. Finally, you also can multiply this out and write these functions, double check that work there. It's pretty simple. It's in this form that it's easier to linearize about equilibrium points. Okay? When you linearize in particular around the origin, for example, you just get rid of the nonlinear terms. The corresponding linearized system near the origin is dx dt equals 10x, dy dt equals 8y. The origin is a real source. Solutions move away from the origin as t goes to it gets larger because those coefficients of x and y are both positive. Okay, that's something you should know from the past. Linearizing about other equilibrium points, we've got 3 other ones evidently, requires something called the Jacobian matrix. Okay, you can also do change of variables, but that ends up being kind of a pain. My students, you should be able to do change of variables still, but probably for a simpler example. To start the problem, I say note the equilibrium points are these 4 points right here. And I tell my students you do not have to confirm this, though if you were, you should be able to if I did ask you to. Let's do it as quick as possible in our heads for the first 3 at least. Certainly if x and y are both 0, then these 2 right-hand side functions are both 0. So dx dt and dy dt are 0. X and y do not change. 0, 0 is an equilibrium point. What about this next one? That occurs when y is 0. Y is 0 makes this right-hand side equal to 0. And, well, with this right-hand side, if you plug in y equals 0, x could either be 0, but we've already taken care of that, or 10 minus 2x could be 0, so x would be 5. 5, 0 is another equilibrium point. With this one, x is 0, y is 4. X being 0 makes this right-hand side 0. What about this one? If x is 0, this is going to be 0, either if y is 0, but we've already taken care of that, or if 8 minus 2y is 0, in other words, y is 4. The last equilibrium point here, 20 11ths, comma 14 11ths, occurs when both these things in the parentheses are 0. You'd have to solve a linear system of equations. Set that equal to 0. We could write it as 2x plus 5y equals 10. Set this one equal to 0. Careful, the x and y are in the opposite order here. We could write that as 3x plus 2y equals 8. If I asked you, my students, to solve for this 4th equilibrium point, you should be able to do this. Solve this linear system. You should get this answer, okay? I won't take the time to do that for this video, because now we're on to part A. Find the Jacobian matrix, J, at this 4th equilibrium point, and then use it to write down what's called the linearized system near the point, where I use a new variable, u, to represent that linearized system, and I'll try to explain what's going on there here in a little bit, for some linear function L. Okay, so you got to know about this. What is the Jacobian matrix, first of all? In general, it's a matrix that's a function. It's a function of x and y. We're going to plug in the equilibrium point. You find that function by creating a matrix whose first row consists of the partial derivatives of the first right-hand side function with respect to the first variable and the second variable. Partial derivative of f with respect to x and partial derivative of f with respect to y. And whose second row are the corresponding partial derivatives for the second right-hand side function, the g function. Partial derivative of g with respect to x, partial derivative of g with respect to y. When these functions are expanded, that makes the derivatives easier to calculate. So I need to differentiate first this one with respect to x, treat the y as a constant. Partial derivatives symbolically are no more difficult than ordinary derivatives. Pretend the y is constant here. I get 10 minus 4x. Differentiate this with respect to x, treating the y as constant, gives negative 5y, right? Treat the y as constant. There's not anything to do with implicit differentiation here. Y is not a function of x when I think about that. For the next one, the partial derivative with respect to y, treat the x as a constant. Differentiate with respect to y, get 0 minus 5x. Let's do the lower right one next because that's going to be longer. Derivative of g with respect to y, treat the x as constant, gives me 8 minus 4y. Differentiate that with respect to y, treat the x as constant, minus 3x. And finally, the lower left is the derivative of this with respect to x, treat the y as constant, 0 minus 0, negative 3y. So there's the general Jacobian matrix. So the Jacobian matrix at the equilibrium point, I've got to plug in these numbers. X equals 20/11, y equals 14/11. Not the most pleasant thing to do, but bear with me here. Replace x with 20/11 there, I'll get minus 80/11. Replace y with 14/11. 14 times 5, can I do that in my head? 70/11. Yeah, 70. This one, I get a negative 5 times x is negative 5 times this is negative 100/11. Let's do the lower right one again. Next, 8 minus 4y. Careful, there's the y. 4 times 14 is 56. Minus 3x, minus this, times 3 is minus 60/11. And lower left corner is negative 3y. Negative 3 times 14 is 42/11. Get a common denominator of 11 everywhere. 10 is 110/11. 110 minus 80 is 30. Minus another 70 is negative 40. And we also need to compute this one. 8 is 88/11. 88 minus 56 is 32. Minus 60 is negative 28. Hopefully no mistakes there. That would be the Jacobian matrix. So we did part of part A. What's the other part? Write down the corresponding linearized system. du dt equals L of u, where L is some linear function. Really a linear transformation. What linear function? Just the Jacobian matrix times u, right? We create linear transformations in higher dimensions as matrices times vectors. That's the matrix we want. J of 20/11, comma 14/11 times u. So that becomes negative 40/11, negative 100/11, negative 42/11, and negative 28/11 if I've not made a mistake, times u. I could go ahead and write a u here. I could also write components if I want, maybe. Maybe call them little u and little v instead of vector u. That's okay. What does u represent here? It represents essentially a change of coordinates that translates the origin to this point right there, which this is the point with coordinates 20/11, 14/11. 20/11 is a little less than 2. 14/11 is a little bit bigger than 1. Essentially, a new coordinate system centered at this point. It becomes your new origin. A u-axis going this way, say, and a v-axis going this way, say. I'm not going to draw it because that would mess up the picture, but that's the basic idea. The Jacobian matrix is a kind of higher dimensional derivative found by combining these partial derivatives in this way. It's a derivative of the vector field, you might say. All right, that's part A, all of that. On to part B. Use the Jacobian matrix to determine the nature of the equilibrium point at 20/11, 14/11 of the original nonlinear system. With some extra directions, you can either focus on the eigenvalues or something called the trace determinant plane. The trace determinant plane is quicker. The trace and determinant of this matrix, in most cases, completely determines the behavior of these solutions near an equilibrium point. It's called the Hartman-Grobman theorem. I'm not going to state that. In most cases, as long as your eigenvalues don't have zero real part, either they're not the number zero or they're not purely imaginary, as long as that's the case, then the equilibrium point will be what's called hyperbolic, and the linearized system will tell you what the behavior is. Now, you can actually just look at this vector field here and see it looks like this is going to be some sort of saddle point. And it turns out it's enough to confirm that the determinant is negative to confirm it's a saddle point. But let's go ahead and compute the trace and determinant anyway. The trace is the sum of the numbers in the main diagonal, so that's negative 40 elevenths plus negative 28 elevenths is negative 68 elevenths. And the determinant, 40 times 28. Oh, I should be able to do that in my head, huh? 1120 over 11 squared is 121. Two negatives make a positive, minus the product of these two, which will be minus a positive number. And that's 100 times 42, so 4200 over 121. Yeah, the determinant is negative. And that's really all that matters. In the trace determinant plane, this point with these coordinates is down here. And all that matters actually is it's below the t-axis, where d is negative. That's enough to say that this linearized system has a saddle point at the origin, and because, in terms of eigenvalues, there'd be one positive real eigenvalue and one negative real eigenvalue. And that's enough to say it's also hyperbolic, and the Hartman-Grobman theorem would say that this point must be a saddle point, and you can see it does look like a saddle point. So the answer is saddle point. If d were positive, it gets more complicated. If you're over here, where t is negative, the point would be some sort of sink. If you're over here, where t is positive, it would be some sort of source. And there's something called the repeated root parabola that has equation d equals t squared over 4 that determines whether or not it's going to be a spiral sink or a real sink, non-spiral, or spiral source versus real source. It's spiraling when the point whose coordinates are t and d is up here or here, non-spiraling over here and over here. Anyway, part C, use the vector field and the null lines to help you sketch some representative solutions. Yes, these lines that I drew in here are null lines. They come from setting dx dt and dy dt equal to 0. The x null line is where dx dt is 0, where this is 0, which is either at x equals 0, the y-axis. Notice along the y-axis, the vector field is vertical here and going up, and vertical here going down, and going down over there. Or when this is 0, which can be solved for y as a function of x to get y equals 10 minus 2x over 5, which would be 2 minus 2/5 x. That's this line here, and notice the vector field is vertical along that line. It's not a straight line solution. It's a null line. The vector field has null x component in this case. For the other ones, that's where dy dt is 0. That's called the y null line. Either y is 0, which is the x-axis. The vector field is horizontal along the x-axis. Or when this is 0, which if you solve for y as a function of x is y equals 8 minus 3x all over 2, which would be 4 minus 3/2 x. 4 minus 3/2 x. That's this line. The vector field is horizontal along there. Where distinct null lines cross, you get equilibrium points. There's 4 of them. Now draw in other solution curves. If you pick an initial condition, say up here, it's pretty clear. You follow those arrows. It's going to go down this way. It's got to cross this y null line with a horizontal tangent. And then you're forced to head up toward this equilibrium point. By the uniqueness theorem, distinct solution curves cannot touch, and so you can't cross this y-axis here, and in fact there's a straight line solution along the y-axis going upward here and downward here. If your initial condition is down here a bit more, looks about like this. Over here, looks about like this. Over here, looks about like this. Got to cross that x null plane with vertical tangent. Down here, solutions look about like this. And yeah, these solutions don't touch each other. They get really, really close together, arbitrarily close together, but they don't touch each other. They do all approach, the ones that are over here approach this equilibrium point as t goes to infinity, and the ones that start down here approach the other one as t goes to infinity. Not expecting perfection in your drawings, but decent. Should certainly cross the null planes correctly. These solutions do approach the origin as t goes to minus infinity. They never touch it, but they do approach it. Likewise, they never touch these equilibrium points either as t goes to plus infinity. They just approach them. And hopefully it's intuitive that somewhere, for example, in here, there's got to be some initial conditions that, well, don't necessarily send you straight toward this equilibrium point, but close to straight. About like that. Another one's down here that go close to straight toward that equilibrium solution as t goes to infinity. These are separatrices, plural of separatrix. There are two of them. I'm supposed to draw four of them, four separatrix solutions. Why are they called separatrices? Because they separate the plane into initial conditions with different long-term behaviors. Solutions with initial conditions down here head toward this equilibrium point as t increases. In other words, y dies off and x grows toward a stable value of the carrying capacity. Solutions with initial conditions up here head up toward that one. X dies off and y heads toward its carrying capacity. Would you ever observe a separatrix in real life? Probably not, right? It's too unstable, you might say. If you start on just barely on either side, different long-term things can happen. It's kind of an unstable type of situation. So you probably would never actually observe that, or if you did observe it, it would just be very close to the separatrix without actually equaling it. You'd have solutions going like this. And that is also emphasizing that the point here, this equilibrium point, does look like a saddle point. And there's other two separatrices going away from this equilibrium point as t grows, like this, and one down here like this. Those are the two other separatrices of the four separatrices. And again, other solutions look like this. Okay, so that's a halfway decent picture of the phase portrait for this nonlinear system. And the moral of the story is, if this model is accurate, one or the other of these species is going to die off and the other one will head toward its carrying capacity. Again, you probably would not see the situation where they both live in a stable harmony here. Is that realistic? Probably not, right? This vastly oversimplifies real life. So you might wonder if it's approximately realistic. That's a possibility. Exactly is probably too much to expect. Certainly a moral of the story, you might say, in that it's possible for one species or the other to die off. All right, this is our one parameter of family of linear systems with a parameter A. Right? This is not just one equation, it's infinitely many equations, and we're going to analyze them all at once. Yeah. We will, by thinking about the trace determinant plane again. Part A says, sketch the corresponding curve in the trace determinant plane. What's the corresponding curve? Figure out how the trace and determinant depend on A, and then plot that as a parametric curve in a TD plane, a plane whose axes are labeled T and D for trace and determinant. It's easier to do than it sounds. The trace is a function of the parameter. I'll write T equals T of A, even though that's abuse of notation. Add up the numbers on the main diagonal. 2 plus A minus 2 The 2's cancel. That simplifies to a. How nice. And the determinant is also a function of a. 2 times a minus 2 minus 1 times negative 7. Okay, that's going to be 2a minus 4 plus 7 is 2a plus 3. Okay, so now plot the corresponding parametric curve. You could just plot some points. You also could eliminate the parameter. Since t does equal a here, you could replace this a with t and say this parametric curve is along the line in the TD plane with equation d equals 2t plus 3, a slope of 2 and a vertical intercept of 3. Though keep in mind it is a parametric curve, it gets traced out in a certain direction as a increases. In this case, as a increases, both t and d increase, so you're going to get traced out going in the usual way, left to right and low to high. Here's what I mean. So the trace determinant plane. By the way, in part B, we're going to sketch on top of that different types of behaviors, like sink, source, saddle point, that kind of thing. So I'm going to make my picture fairly large here for part B. I'll include part B as well, I guess is what I'm saying. A fairly large trace determinant plane, TD. So this is A and B. One critical locus is the t-axis. When d is negative, for example, like I mentioned before, that means the origin is going to be a saddle point. As you cross this t-axis where d is 0, a bifurcation occurs. Another critical locus, which I did not mention before, is the positive d-axis. When you're on the positive d-axis, it turns out, and you're not at the origin at least, that you have purely imaginary eigenvalues. And what that ends up meaning by Euler's formula is that your solutions have cosines and sines involved, but no exponential growth or decay. And the origin is what's called a center, sort of the boundary between a spiral sink and a spiral source. And then you've got this repeated root parabola. Its equation being d equals t squared over 4, equivalent to t squared equals 4d. And that's the boundary between spiraling and not spiraling, which I hinted at with the other problem. The line with equation d equals 2t plus 3 looks about like, well, it depends on what the scale is to where to draw this. Say right about like this, where this is 3 here. And let's see, d will be 0 when t is negative 3/2. This is negative 1.5 right there on the t-axis where t is negative 1.5 and d is 0. And as a increases, the motion along this is upward and to the right. It could have been the opposite, though, so you got to be careful. Bifurcations occur when you cross critical loci. So right here, right here, right here, and well, it's not drawn, but it would also occur up here. There's going to be 4 bifurcation points. These are what I call analytic bifurcation points. A topologist, I talk about that here, doesn't care about spiraling versus not. That's a little bit of an exaggeration, but so a topologist would not care about transitioning from non-spiral to spiral or vice versa, but we will. As far as doing part B now as well in this picture, sketch typical behaviors. Down here again, it's a saddle point. I could write the word saddle. I could also make just a quick drawing of a generic saddle point. Say something like this. In here, it's a real sink, turns out. With no spiraling, the origin is going to have two straight line solutions, two sets of them. You might get some sort of picture about like this. In here, you've got a spiral sink. Will it spiral clockwise or counterclockwise? I'm not going to take the time to figure it out. It actually is going to be clockwise. I can tell by looking at the first column of this matrix. I'll leave it to you to figure out why. Over here, it's going to be a spiral source. And up here, okay, if this were an exam, I'd maybe redraw this. It's going to be a real source. Say something like this. Generic kind of picture. Oops. Dropped my pen, or my pen cap, I guess I won't worry about it. Part C. Two of the bifurcation values are -3/2 and 0. Why? When we cross one of the critical loci, that's where bifurcations occur. We're going to cross the positive d-axis when t is 0, in other words, when a is 0. We're right there when a is 0. A equals -3/2 is when we cross the t-axis where d is 0. Set d equal to 0, 2a plus 3 equal to 0. Get 2a is -3, so a is -3/2. That's another bifurcation value. You're right there. Not only is this t equals -1.5, it's also a equals -1.5. That was a lucky thing. It didn't have to happen. So the other two bifurcation values show work to find the other two bifurcation values for an analyst are going to be at this point and this point. This one, a is going to be just barely bigger than -1.5. This one, it's hard to say, some big positive number, relatively big. How do you figure it out? It's crossing the repeated root parabola. Focus on values of a that make that equation true. That's how to find them out. So take that equation for part C here. Replace t with a and replace d with 2a plus 3. To get a squared equals 4 times 2a plus 3 is 8a plus 12. Quadratic equation, a squared minus 8a minus 12 equals 0. Can't easily factor that. The quadratic formula is necessary. Gives 8 plus or minus square root of -8 squared is 64. Minus 4 times 1 times -12 is going to be plus 48. It's not a nice number here. It's 4 plus or minus square root of 112 over 2. It's fine that those are the answers. Can we simplify this? Is this divisible by 112 divisible by 4? Yeah, so it's square root of 4 times square root of, what would it be, 28? 28, 56. Yeah, 28. And that cancels with the 2, so it looks like it's 4 plus or minus square root of 28. That also can be divisible by 4. You could also write this as 4 plus or minus square root of 4 times square root of 7 is 2 square root of 7. So it looks like, if I've not made a mistake, those are the other two bifurcation values. Is one of them the 4 minus one, just barely bigger than -1.5? Yep. And the other one turns out to be about 9.3. Okay? But those are the answers where we are crossing the repeated root parabola. Forgot a Mathematica here, which I was going to show you earlier. This was the competing species model, the Jacobian matrix, and there's the matrix and its determinant, which can be simplified Okay. Here, okay, this is worth looking at. Here's an animation of the stream plot, which shows solution curves for this problem we're looking at right now. As a increases, starting at -5, you can see the origin as a saddle point. As a crosses -1.5, it very briefly converts to a real sink. It's tough to tell that's a real sink, but it is. And then it becomes a spiral sink. That's easier to tell right there. When a crosses 0, it becomes a spiral source. Now it's a spiral source. And then eventually it becomes a real source, though I think I didn't let a get large enough. No, I did. Okay. It eventually becomes a real source here when a gets past 4 plus 2 square root of 7. Okay, so kind of a pretty transitioning of the phase plane as a increases. All right, next problem. 2 more pages here. One of them, once again, it's a problem that looks long. This one, well, okay, one part of it is a little long, but the rest is fairly quick. This is related to linear algebra as well. So you might not get this in your differential equations course. On the next page, however, you might get some things that I have there about Hamiltonian and gradient systems, especially. Even if you don't know about linear algebra and diagonalization, it's probably still worth listening to and learning about. I'm teaching this in the context of a differential equations and linear algebra class, and so I want to relate differential equations to linear algebra, besides just the basics of eigenvalues and eigenvectors. What I have here is called a symmetric matrix. And that means its transpose is itself. And what is the transpose? The transpose of this 2x2 matrix is another 2x2 matrix whose first column is the first row of this matrix, and whose second column is the second row of this matrix. So the first row of this matrix, -2, 5, becomes the first column of the transpose, -2, 5, which this already is, because this is symmetric. And the second row, 5, -2, becomes the second column. So because the first row of this matrix equals its first column and the second row equals its second column, if you actually flip them, this is symmetric. You're guaranteed that these two numbers have to be the same. These two numbers happen to be the same in this example, but they don't have to be in general. Though making them the same makes the math easier in the calculations with eigenvalues, for example. Part A says, show work with eigenvalues and eigenvectors to come up with what's called an orthogonal matrix P, so that this product, P transpose times AP, is a diagonal matrix, where the only non-zero number is on the main diagonal. That's what diagonal matrix is. An orthogonal matrix has columns that are called orthonormal, which means they're orthogonal. They're perpendicular to each other as vectors. Their dot product is 0, and also normalized to have a length of 1. Orthogonal matrices are very special, and they do have the property that their transpose equals their inverse. Usually when we do a change of variables for diagonalization, you put a P inverse there instead of P transpose. But with an orthogonal matrix, you can put a transpose. There's something called the spectral theorem that says when A is symmetric, like this one is, that you can always do this. Okay? That's based on some theory. All that is preamble just to say we want to figure out what P is. Okay. Part A is probably the longest part. Well, part E is a little long, but find eigenvalues and eigenvectors. The general characteristic polynomial for a 2x2 matrix is lambda squared minus the trace times lambda plus the determinant, where lambda is an unknown quantity that can be solved for and gives you the eigenvalues when you solve for it. The trace of this matrix, sum of the numbers on the main diagonal, is -4. So if I do minus the trace times lambda, I get actually plus 4 lambda. And the determinant of this matrix is going to be negative. 4 minus 25 is -21. To find the eigenvalues, set this equal to 0 and solve for lambda. This actually can be factored. It's a nice example. It can be factored as lambda plus 7 times lambda minus 3. So the eigenvalues are -7 and +3. These are going to end up being the numbers in the main diagonal of D, the diagonal matrix we're after. We've got to find the eigenvectors. For -7, what do we get? We need to think about a minus lambda I, so that's a plus 7I, where I is the 2 by 2 identity matrix. Imagine adding 7 times I to this matrix. Effectively, you're going to keep the off-diagonal numbers the same and add 7 to the main diagonal numbers. We're going to get 5, 5, 5, 5. And the corresponding system of linear equations to solve for the eigenvectors is 5x plus 5y equals 0 and 5x plus 5y equals 0. It's a redundant system, as it has to be to find eigenvectors. Either of these equations can be solved for, say, y in terms of x or x in terms of y to find eigenvectors. I'll solve for y in terms of x and think of x as a free variable. Take, for example, x to be 1, then y is forced to be -1. Any non-zero multiple of this works as well. For lambda equals 3, the other eigenvalue, we compute a minus 3i. It's always a minus lambda I. In this case, that became a plus 7i. In this case, it becomes a minus 3i. So I subtract 3 from the numbers in the main diagonal and leave the off-diagonal numbers as they are. This corresponds to this system. And while those equations are not the same, they are redundant. They both imply y equals x, and they both imply then I can take eigenvectors to be any non-zero constant multiple of 1, 1. These vectors are orthogonal. Their dot product is 0. But they're not normalized yet. For this one, its length is the square root of 1 squared plus -1 squared is the square root of 2. And for this one, its length is also square root of 2. That's symbol for the magnitude of v there. Length of v is also square root of 2. In that case, that happened to happen here. It doesn't have to happen, right? I mean, I could have picked 2, 2 here, and then the length would be square root of 8. So it didn't have to happen that those lengths are the same. But what I do now is to create the matrix P, that's going to be an orthogonal matrix, is I use these as the columns of P once I've normalized them, once I've divided them by their length, square root of 2. So the first column of P is going to be 1 over square root of 2, -1 over square root of 2. Divide both of those things by square root of 2. And the second column is going to be what I get when I divide both of those by square root of 2. And it turns out this is an orthogonal matrix, which means not only are its columns orthogonal to each other as vectors, but they are also normalized. It probably would be better to call it an orthonormal matrix. This is orthogonal. And that does imply, and you can check this, that its inverse equals its transpose. It's not a symmetric matrix, so the transpose is different. I have to make this first row the first column, and make this second row the second column. So it's not a symmetric matrix. By the way, this answer for P is not unique. I also could have switched these columns around, and then I would have gotten a symmetric matrix. But if I want -7 to sort of be the first eigenvalue and 3 to be the second in the diagonal matrix D, then I should do it in this order. I also could multiply this one by any non-zero. Well, okay, I could multiply by -1, and I could put the negative sign up there instead, and that would end up being actually a symmetric matrix as well. But this is fine. And that is the answer to part A. That's what we're after. You don't actually have to calculate D, but if you want to take the time to check it, D equals P transpose AP, you could take the time to check, is a diagonal matrix whose numbers on the main diagonal are -7 and 3. So it's this matrix right there. And that's worth knowing, and we might even need it. In fact, yes, we do need it for part C. I guess I'm doing part B right here. What is P transpose? Write it down. It's right there. If I had picked a different, if I had picked a different initial equivalent answer, it would have been something different, possibly even equal to P itself. And part C, what is the matrix D? You can just state D without doing any computations. It is this matrix. You just got to know the numbers in the main diagonal are going to be the eigenvalues in the same order that came with the eigenvectors. If this is the ordering for your eigenvectors, then you got to get the same corresponding ordering for the eigenvalues. If you switch these two columns around, then you'd actually have a 3 there and a -7 down there. Part D, write down an abstract formula for something called the matrix exponential. So I'm also testing on matrix exponential. If you don't know what that is, okay, I'll explain it a little bit. In terms of the matrix exponential e to the TD, P and P transpose. Okay. Matrix exponential is e to a matrix power. It's defined by a Taylor series, which I don't want to take the time to find, but it helps you solve the differential equation. That's its purpose. In fact, you could say the solution of the differential equation dy dt, d vector y dt equals a times the vector y that satisfies an arbitrary initial condition, say y of 0 equals y sub 0. The answer for the solution is y of t equals e to the ta times y0, where e to the ta is this matrix exponential, e raised to a matrix power that can be defined by Taylor series. This does end up being a matrix times a vector, okay, without going into details. The matrix exponential can be very difficult to compute in general. However, when you can diagonalize the matrix A, then it can be done. Oops, I guess I already had a D there. And how is it done? E to the TA first gets rewritten by rewriting A in terms of D. Now, since D is P transpose times AP, which in general, again, is P inverse times AP, you can take this equality and multiply both sides of it on the left by P to cancel the P inverse there to get PD equals AP, and then multiply both sides of it on the right by P inverse to cancel the P there and say PD P inverse equals A, which for when P is orthogonal is the same as PD P transpose equals A. So what I can do is I can replace the A with PD P transpose. And it turns out through some theory that takes proof that this ultimately ends up equaling P times e to the TD times P transpose, which again is P inverse. And that does it, actually. That's an abstract formula for this matrix exponential in terms of these matrices. That is all you need to do to solve part D. I will comment before we do part E that e to the TD is easy to calculate. It turns out that because D is diagonal, this is easy to calculate. You just take D and you make the -7 and the 3 part of the exponent of E as well as T. E to the -7t, 0, 0, and e to the 3t turns out to be what this matrix exponential equals. And then you do this multiplication to find this matrix exponential, and then that helps you solve the initial value problem. Is the purpose of all. Part E, show details of calculations with scalar equations or with matrices, including calculations with numerical entries. Don't be abstract here. To confirm that this change of variables converts this system to a diagonalized system, also called completely decoupled. Wow, what's that about? Actually, let me do the abstract calculation first, even though that's not what's requested. du dt, where u is defined by these equations, you can think of it either way. And again, P is orthogonal, so P transpose is P inverse. In general, this would be a P inverse there. Well, by this equation, P and P transpose are constants, so you just differentiate the y. This becomes P transpose times the derivative of y with respect to t. But the derivative of y with respect to t is a times y. I'm assuming y satisfies this differential equation. But y can be replaced by p times u, pu. And then associative property allows you to write this. And that matrix right there is D. So that is an abstract derivation of the fact that this system gets converted to this system where D is a diagonal matrix, and that means the system is completely decoupled. But that's not the directions. That was worth doing, but it's not directions. The directions are work with scalar equations or matrices, including the numbers that are involved. Let's take a little bit of time here. Hang on, I can do it pretty quick. Again, this is the abstract approach. The abstract approach is actually easier when you know how to deal with these equations. What about the scalar approach? I'm going to have a lowercase variable u and a lowercase variable v, say, as the components of the vector capital U. Du dt, where does that come from? That comes from the fact that u is p transpose times y. U is p transpose times y. In other words, the vector whose components are uv is p transpose is this matrix here. 1 over root 2, negative 1 over root 2, 1 over root 2, 1 over root 2, times a vector whose components are, say, little x and little y. So du dt, because u is going to be 1 over root 2 times x minus 1 over root 2 times y, multiplying this matrix times this vector, du dt is going to be 1 over root 2 dx dt minus 1 over root 2 dy dt. What are dx dt and dy dt? They come from this equation. A times y, where A is this matrix. Don't forget about that matrix. So dx dt is negative 2x plus 5y. Negative 2x plus 5y. That's what I'm trying to write there. That's with a positive sign, sorry. Minus 1 over root 2 dy dt. What is dy dt? Go back to the original matrix. Look at the second row. It's 5x minus 2y. Imagine multiplying that times the vector xy. We can simplify. The x terms give you, just double checking things here. Negative 2x over root 2 minus another 5x over root 2. That'll be negative 7x over root 2. Negative 7. Where have I seen that before? There. Huh? Although this root 2 seems to be throwing a fly in the ointment, but it will go away, actually. With the y term, I got a 5y over root 2 and a plus 2y over root 2 is plus 7y over root 2. I want to get back in terms of u. So I need to substitute again. Replace x with something involving u and v based on this equation, where p is this. In other words, it's x is 1 over root 2 times u plus 1 over root 2 times v. And y gets replaced by thinking about the second row here, negative 1 over root 2 times x plus 1 over root 2 times y. Oops, u and v, sorry. U and v. The v terms cancel, because you got negative 7 over root 2 times positive 1 over root 2 v, and positive 7 over root 2 times positive 1 over root 2 times v. The v terms go away. The u terms give negative 7 halves u and another site negative 7 halves u, which is minus 7u. For the sake of time, I'm not going to completely do the other one. dv dt, based on this equation again, u equals p transpose times y, and the fact that p transpose equals this, I'll do the first step. Look at the second row. This is going to be 1 over root 2 dx dt plus 1 over root 2 dy dt, not minus. You can check in the end. This should simplify to 3 times v. So the original linear system, when it's diagonalized with a new change of variables, becomes a diagonal system that's completely decoupled. du dt equals negative 7u and dv dt equals positive 3v. Very easy to solve, either in terms of matrix exponential or just by guessing. You deserve an award if you're still watching. This is the last page. I'm going to look at mathematical a little bit more as well, but that'll go pretty quick. True, false, and multiple choice. Number 5, use linearization to classify the equilibrium point for this nonlinear system. Do notice that 1, 1 is an equilibrium point. Makes both right-hand sides 0. Using linearization means, well, if this were the origin, we just throw away the nonlinear terms, which would mean just throwing away that minus x squared. But if it's something else besides the origin, I need the Jacobian matrix. Partial derivatives. First row, the first entry is the partial of f with respect to x. Treat the y as a constant, negative 2x. Second entry is the derivative with respect to y, which is 1. Second row, look at g. Its derivative with respect to x is 1, and with respect to y is negative 1. There's your general Jacobian. Plug in 1, 1. Classify now. Trace and determinant. Trace is negative 3. Determinant is 2 minus 1 is 1. In the trace determinant plane, we are over here somewhere, probably below the repeated root parabola, it looks like. So it looks like the answer is going to be the origin, this 0.11 is a real sinc. D is probably the answer. If you wanted to be sure, you might want to actually solve for the eigenvalues with the characteristic polynomial. There it is, set it equal to 0, use the quadratic formula, negative 3 plus or minus square root of 9 minus 4 over 2. Yeah, those are real eigenvalues. And yes, both negative. The origin is a real non-spiral sinc. The answer is D. Technically, I'm using this Hartman-Grobman theorem that I haven't stated. This one's true, false, and related to a Hamiltonian system. What is that? I'll mention what a Hamiltonian system is in number 8. I probably should have switched these around. For the moment, for this true-false question, all you need to know is, yes, this is very much true. For a two-dimensional system, Hamiltonian system, solution curves lie on level curves of the Hamiltonian function, where the h of xy equals some constant. That's true. Okay, that's a fundamental fact to know about Hamiltonian systems. 7, for a fixed value of the spring constant q, the graph of the amplitude a of omega of the force response of this damped forced harmonic oscillator has a maximum value, a peak that increases as damping increases. You got to know something here too. Basic idea is that, going back to the very first problem, the force response, the steady state solution, yp, when you got damping, well, even if you don't have damping, well, with damping it is the steady state. Other solutions are going to decay it to 0, the other parts of the solutions. And if you imagine changing the frequency excuse me, of the forcing function, the cosine of omega t, that affects the amplitude, the capital A, from the problem 1, the distance of little a from the origin, the complex number little a. It turns out the graph of this typically looks, of this A as a function of omega, typically looks about like this. It doesn't oscillate. It increases toward a peak, then comes back down and heads towards 0 as omega increases. But we're not thinking about omega increasing. We're thinking about P, the damping, increasing. This is a graph for some fixed value P. The question is, what happens to this maximum point as P increases? I hope it's intuitive that the more damping you have, it's going to damp out even the forced response. It should go down. The maximum point here of this graph should go down as P increases. That means this is false. It doesn't increase, it decreases. I'm not proving that. You're just trusting me on that. That is the background. When P is, on the other hand, when P is small, very small amount of damping, practically an undamped harmonic oscillator, you can get what's called resonance. You can get very, very big oscillations. The forced response can have a very big amplitude. This graph can be very steep and extreme when P is very small. So when P increases, the peak tends to go down. It tends to decrease, not increase. This is false. What is a Hamiltonian system? That's what number 8 is about. 9 is the last question, by the way. Do you want to, again, see Mathematica, though? I'm saying this is Hamiltonian. That does mean the right-hand side of the dx dt equation is the partial derivative of some function h with respect to y. H is called the Hamiltonian function. And the right-hand side of the dy dt equation is the opposite of the partial of that same function with respect to x. I'm saying that's definitely true here. If it were a question of is it Hamiltonian or not, the way you can check is you can take the partial derivative of f with respect to x and the negative of the partial derivative of g with respect to y and see that they're the same. And if h is a nice function, they will have to be the same by something called Clairaut's theorem about the equality of mixed partial derivatives of h with respect to x and y. Anyway, these are both 1. They are the same. It is Hamiltonian, no matter what point we're at. These don't depend on x or y. As far as finding the Hamiltonian function, we need to think about these facts, and we essentially just need to integrate. For example, we can take the first equality here and integrate with respect to y, treating the x as constant, and get x times y plus y cubed plus some constant in y that could be a function of x. Call it psi of x or something. That's an integration constant with respect to y, but it could depend on x, because when you differentiate this with respect to y, that differentiates to 0. And these two do differentiate to x plus 3y squared. I also want this, so this is essentially what h looks like, which does mean it looks like the answer is either B or D. I also want the second one to be true. What's the opposite of the partial of this function with respect to x? Derivative with respect to x is going to be y plus psi prime x. So this becomes negative y minus psi prime x. I want to set that equal to what I see here, negative 2x minus y. The minus y is already matched, and therefore psi prime of x, to make these equal, is 2x, and psi of x can be taken to be x squared. Plus any constant, plus any actual constant works. But anyway, the fact that psi of x is x squared, plug that back up into here, means the answer is B. Any constant added to that would work as well. What is the Hamiltonian function here? In applications, it often represents total energy. And it turns out that because of these facts, it turns out total energy will be conserved. You can check on your own, I will not take the time to do so, that the derivative of the Hamiltonian function with respect to time along a solution curve, if this is a solution curve I'm plugging in, is 0 for all t. You need the multivariable calculus chain rule to do that, plus the differential equations. I'll leave that to you to figure out if you are interested. Let's go ahead and look at Mathematica quick for this problem. The Hamiltonian function for this problem can be taken to be this. And what we're seeing here is, first of all, level curves of the Hamiltonian function. Secondly, solutions in blue that lie on top of the level curves of h, where h is constant. Okay, but you need technology to be able to see that. Last problem. The following is a gradient system. What does that mean? And this is true, false. That means if it's true, let me put question marks here. Question mark, question mark. If it's true, that means there's some function often called v, where this is the partial of v with respect to x, and this is the partial of v with respect to y. To determine if it is, I use Clairaut's theorem effectively again. I now differentiate f with respect to y and g with respect to x and see if I get the same thing. It's really more than Clairaut's theorem that would be necessary to prove that's good enough. But are these equal? Partial of f with respect to y, treat the x as constant. It's negative 6x. Partial of g with respect to x is also negative 6x. Those are equal, no matter what the point is. The answer is true. Could I find v? Yep, you can do it by integration again. And I did it in Mathematica. And it turns out this can work for v. You can double check that. Found it by integration again. Now the solutions don't lie on the level curves of v. They are orthogonal to them. So these background curves are the level curves of v, where v is constant, and the blue curves are solution curves. You can see that they're crossing the level curves of v orthogonally with a 90-degree angle, a 90-degree tangent line every time they cross. There are a couple equilibrium points right about here and here at 1, 1 and negative 1, negative 1. But the answer here was true. This was a gradient system. It is the gradient vector. The vector field is the gradient vector for some function v. V is called a potential function in this context. Wow, a lot. Thanks for watching.